Our group focuses on developing advanced characterization techniques to study the surface chemistry and ion transport in technologically important materials, such as rechargeable batteries, capacitors, fuel cells, and solar cells. Research activities in our group include material synthesis, surface modification, device fabrication, performance testing, characterizations, and first principles calculations. The following video provides an overview of these activities using our studies on rechargeable lithium-ion batteries as an example. Most electrode materials are synthesized using solid-state synthesis method employing high-temperature furnaces. Other methods, such as hydrothermal synthesis, sol-gel, and molten salt, are also employed to fine-tune the particle size and morphology of electrode materials. The active electrode materials are mixed with polymer binder, conductive carbon matrix, and solvent to form a slurry. Then the slurry is casted onto a carbon-coated current collector, often copper or aluminum foil, using a doctor blade to form electrode films. Thickness of the film can accurately be controlled on the micron scale. Then the film is cut to the desirable size for making rechargeable batteries. Battery components are sensitive to oxygen and water. Therefore, battery fabrication is carried out inside an argon-filled glove box with controlled atmosphere. Batteries are composed of 3 parts, including 2 electrodes and electrolyte in between. The 3 components are encased in different packages depending on the battery type. We are showing here the fabrication process of coin or button cell batteries. These measurements are carried out to test the energy density, the rate performance, lifetime, and cyclability of rechargeable batteries. We employ advanced solid-state NMR spectroscopy and imaging to track changes in structure and ion dynamics of materials and devices. We perform in situ characterization of batteries by charging and discharging the batteries while acquiring NMR spectra in real time. In this case, we are able to catch transient processes that only exist within a very short time. Alyssa is demonstrating how she sets up an in situ experiment by placing the bag cell battery inside the NMR probe, connecting the battery to the battery cycler and NMR probe connection for data acquisition. Shang is showing NMR experiments in high magnetic fields. Most of the NMR probes are home-built with unique capabilities that are not commercially available, which allow us to carry out novel and original research.
记得啦。好，来。好来。好啊。就左右乱调这样。
Dynamic nuclear polarization, or DNP, is an emerging technology which permits sensitivity enhancement by hundreds of times compared with traditional NMR. It represents the state-of-the-art NMR instrumentation. We are exploring the use of this $3 million equipment to further our understanding of surface chemistry. We use first principle calculations to assist with our understanding of structure and dynamics of energy materials. Via our research, we aim to address critical questions such as degradation, slow rate performance, low energy density of energy devices, and propose strategies to improve the overall performances of energy devices. You are welcome to discuss your interests regarding specific research projects with Dr. Hu in any